So let me start with the big picture. Two of the most difficult problems in the foundations of physics, or at least they seem to me two of the most difficult and most puzzling, are one, what gave rise to the era of time, and two, what is ontology of quantum mechanics. And it was thinking about these two issues that led me to density matrix realism and to the theory called Wentaculus. Why is that? Well, there are certain answers to these two questions. What gave rise to the era of time? The past hypothesis. But there's some kind of philosophical issues here beside the questions, it's not even false, beside the question that it's not complete, beside the question that it's not specific enough, the questions of philosophical nature, that is, does it have the status of a law of nature? And what kind of law is it? There seems to be some kind of vagueness that's inherent, intrinsic to the specification, but macro state invoked in the past hypothesis. So can a law, fundamental law of nature, be vague? And the second part, that is, we are driven by a bunch of results and also realist theories to think that in some sense, the quantum state of the universe is real. It's quantum state realism. But what kind of realism is it? What kind of thing does it represent in the physical world? Is it a field? Is it a bunch of particles? Is it something else? Is it a law of nature? So there are philosophical worries about how to spell out quantum state realism and the various costs of proposals, interpretations, field, law, and so on. So these worries motivate us to look at these puzzles again. The conventional wisdom says these two puzzles, era of time, quantum mechanics, are independent puzzles, or more or less, conceptually. Are they really independent? Well, I suggest that there exists a new way to understand the second one, the quantum mechanical one, that gives a better way to solve the first one, the era of time. And the key is to evoke density matrix realism. And here's a rough definition of the view that says the quantum state of the universe is objective, it is impure. A more friendly or more, tolerant version would say it can be pure or impure. But I want to make sure that's distinct from wave function pure state realism. So just kind of cross out and make it is. It is impure, it is an impure objective quantum state universe. It is the unique quantum state universe. Okay. So in this talk, I want to discuss a new way of thinking about time's arrow in the quantum universe that attempts to give a more unified solution to both puzzles. And I claim that, I try to provide some arguments, the solution is much more satisfactory than certain answers of the past hypothesis and pure state realism. And it has interesting implications, open question for both physics and philosophy. I call the theory the Wentaculus. I'll explain more in a second why it is called the Wentaculus. I saw David's here, so maybe I'll let him explain. Okay. So I believe that a tree is known by its fruits. The Wentaculus is a fruit of density matrix realism, literally. At least in my mind, when I'm thinking about this project, this is the obvious fruit, low-hanging fruit I can grab. It shows that density matrix realism is theoretically fruitful because it sheds light on two puzzling issues, the quantum state issue and past hypothesis issue. And if I had a different title of this talk, I'll call this the Wentaculus, or how I learned to stop worrying and love the quantum state. Because really, it removed my biggest worry that if I want to be a realist about the quantum state, I want to think of this as something like a law of nature. But the quantum state, pure state, is too complicated, so it cannot be a law. But moving to a density metric realist version and the Wentaculus picture, it becomes suddenly simple because the past hypothesis is simple. And it removes my worry about the past hypothesis that is kind of vague or arbitrary. So the density matrix version actually removes that dilemma of the past hypothesis as well. At this point, I feel obliged to show this picture of Dr. Strangelove, but I'm going to just cross out this called the Wentaculus and the quantum state. Okay. All right, at least that's got a nice memory device. All right, so here's the overview of the talk. 3 parts. Part 1, density matrix realism. Part 2, arrow of time. Part 3, the Wentaculus. I will be spending less time on this 2 and more time on the final part because this was already covered before. Okay, so part 1, density matrix realism. So on my definition, it says the following. The quantum state really of the universe is objective. It can be pure or impure. That's the more tolerant version, right? Let me unpack this for now. So the means the quantum state universe is unique. There are no 2 quantum states, one pure, one mixed. It has a unique one. And the quantum state universe, I would label this as W, the general density matrices. It is objective, but the objectivity of the density matrix is going to be up to debate. Is it something like a field? Is it something like a law? Is it something like something else? Or routine modeling call it something a completely different category of ontology. So that's up for debate, right? Just as wave function realism, what is to be a realist about wave function is up for debate. And that cannot be settled by experiments or observations. So if you have this more tolerant version, you have can be, in a sense, a nomological possibility. The quantum state universe is possible for it to be a mixed state or a pure state, either kind of corresponding to the wave function or an impure density matrix. But I want to make sure this distinguished from wave function realism, so I cross out this part and say it is, or it must be impure. So that's my preferred version. And that's the version I defined also in my 2018 paper in BJPS. Okay. And this theory on my definition of density matrix realism is indebted to many other papers in literature. And primarily to this paper by Rodi and co-authors. I think I learned everything from Rodi, and especially this part of my project is indebted to this paper in 2005, published in Foundation of Physics. And in this paper, as Rodi mentioned, talks about different theories, different roles that rho can play, different roles that density matrix can play in Bohm mechanics. One of the key role is a new theory called W Bohm mechanics, in which it's not a wave function that guides particles, but a density matrix that guides particles. So it's like a pilot density matrix. And there's also the paper by Owen Maroney and the book by David Wallace. So this on the Everettian side. Also this follow-up paper by Rodi and Valialori, Charlie Goldstein, and Neil Zangi, case studies of primitive ontology and different roles of quantum state that can play, published in BJPS. And in this paper, that's the first time I saw WGRW, a theory in which a impure density matrix can collapse and be empirically equivalent to the wave function version, which is super cool, I think, because I thought, well, the obvious way to extend this is by using a master equation and forget about collapse. But no, you have to use collapse, and collapse can be done using a density matrix. So that's really cool. And recently, there was a paper by Katie Robertson, kind of beautiful paper on the Gibbsian side in exploring the rho density matrix and promoting rho and W from subjective to something more real. And this might hold the key to rescue the Gibbsian paradox. Okay. So I recommend it. It's on PSI archive. All right. So a quick review of wave function realism. So on my understanding, the wave function realist theories would be without content, without the specific realist interpretations or theories of quantum mechanics. So you have to give them exact equations of how the quantum state wave function is real. And the part that is real, I think of this as playing dynamical role. So the emphasis on dynamics is important. That is, in different theories of Bohm, Everett, and GRW, what is central to psi, the big wave function of the universe, is that it plays a role in the fundamental equations of motion, fundamental equations of collapse, fundamental equations of the multiverse, and so on, right? And this corresponds I guess in some analogies to the terminology of psi-ontic dynamics that Owen used. And for more, I wrote this paper a while ago on realism about the wave function. I give more options, metaphysical options to understand what the wave function represents. Okay. So in analogy to that, we have density matrix realist theories. And again, we have to fill out the content. The content is given by the laws, the dynamics. On this too, we have available proposals that says it's a W that guides particles. So some gradient of W give you dq over dt, right, in the Bohmian version. And in this one, the W gave rise to the emergent multiverse. And in this one, the W collapses, right? T plus equal to something from T minus, right? Okay. And it's a question of empirical equivalence. So suppose we have wave function realism and density matrix realism, both are coherent positions. Are they empirically coherent? Is there any experiment you can do to decide whether we live in a world in which wave function is real or density matrix is real? And I guess to be more specific, we have to ask, for example, Bohm's version or Everettian version or GLW version. Is the psi version of Bohm empirically equivalent to the W version of Bohm and for Everett and for GLW? And more specific, we should follow what Rodi mentioned, to use a mu Bohm mechanics. That is psi, a random psi, selected from a distribution. And that you can ask some questions and do some mathematics with it. And it's a one-line proof they are empirically equivalent. Although there are, I think, delicate questions to the answer here that I often encounter in discussion about this issue. Anyhow, if it is, I think it is empirically equivalent, then the empirical confirmation for psi theories will also confirm W theories. So here we have an empirical determination by evidence. There's no available evidence that can determine which one is true. And if no, well, that's also good news because now we have different predictions for experiments. Now, the kind of dynamics that Owen was exploring will give rise to different predictions, and what they will be interesting to see. We need more analysis to tease out what kind of experiments we can do. But for me, I want to focus on the empirical equivalent dynamics, interdynamics for Everett and Bohm, and for the GLW case, the dynamics of collapse. Okay, without adding this extra term X. All right. Either way, we have this question of the nature of the quantum state. Either way, whether psi is real or W is real, what does it represent? What does the quantum state represent in the world? What kind of thing is it? Is it some kind of field, as David Albert would argue, right? So psi would be a high-dimensional field on high-dimensional space that gives us some reason to take that space as fundamental, which is very counterintuitive and very radical revision of everyday explanations and experiences, right? And there's worries about that. If W is a field, the fundamental space is not R3n, but isomorphic to R6n, because literally speaking is kind of a configuration of two 3n variables, right? So you have 6n dimensional configuration space being the fundamental space on the Albertian kind of picture. The view I am attracted to is the nomological view, in which the quantum state plays a role like a law of nature. And this is in analogy with the Hamiltonian function in classical mechanics, that H function of phase space is not ontological. It's not a field in physical space or phase space. It is a law. It's kind of on a par with the laws of nature, telling you things how to move. Okay, but unlike H, where H is simple function on phase space variables, the psi and W function on configuration space are dramatically much more complicated. They look nothing like a law of nature. There's so much variations on different parts of configuration space at any time that it's unlikely that any of them is going to be simple enough to be a law. And if you think that's okay, then I probably have to argue with you your notion of lawhood. For me, I have a strict notion of laws that if you have a fundamental law, it's got to be simple, relatively simple at least, right? It cannot be, it's not absolutely simple. That cannot be done, but it's somewhat simple, right? And we know enough about the quantum state, typical quantum state universe, they're not like that. So you have the problem of complexity facing this view. So I was worried for many years about whether I can be a realist if I cannot solve the problem of complexity. I mean, there's fancy philosophy can do about this, and there's fancy physics can do about this. One fancy physics can do about this is to invoke the Wheeler-DeWitt equation, in which perhaps the universal quantum state is stationary, and stationarity might imply some sense of simplicity, maybe symmetries in the quantum state. And that might give you a simple law in the end. But that is not guaranteed. And we don't know, whether it's a unique solution to Wheeler-DeWitt equation and whether the solutions will be simple enough. All right. So part 2, the arrow of time. So we had this puzzle about quantum state. You be a realist, but what is quantum state? The second puzzle is what explains the arrow of time. That is, we see macroscopic irreversibility in our experiences, but we don't have irreversibility in the microphysical laws. They are reversible, backward, forward, essentially, possible. There are some subtleties here about what we mean by reversibility and reversible invariance, but essentially they are reversible. And so an answer to this in the Boltzmannian program is to invoke the past hypothesis that says the universe started in a low entropy state, or one boundary of space-time is such that it is in a low entropy state. I think it is perfectly fine to invoke a law like this. And I actually want to argue that we should take this to be a law and axiomatic status in the theory. So here's the picture you should have in mind. Right, you have the Big Bang state that has a very special initial condition that give rise to typical expansion of the universe and growth of entropy and so on. The usual imagery is the one drawn by Penrose and others, right, with the sharp boundaries on phase space, that you have thermal equilibrium being the biggest state and your passive hypothesis being a small region in phase space in which actual phase point x0 belongs to. But I want to emphasize here that that picture is not only misleading in terms of proportion, but also misleading in terms of precision. There's actually a lot of inherent intrinsic vagueness in the carving out of the boundaries of macro states. In fact, the boundaries of macro states are fuzzy, vague. I mean, I'm exaggerating the vagueness here. The vagueness is kind of small, but still you have vagueness in the boundaries. Along the boundaries, whether this one belongs to this macro state or this macro state is an open question. There's nothing in nature that pins down where the strict boundaries are. Say, even say T equals to 0 degrees Celsius, that seems sharp, but in fact, it is a macro state compatible with a bunch of microstates, and the boundary of that set of microstates is imprecise, it's vague. You can run Schreider's arguments on T equals 0 Celsius and see for yourself that this is vague, but I won't go into details here. Okay. So I do want to maintain that the past hypothesis had this special status in order to perform this role in explanation, second law and the growth of entropy and various structure in our asymmetric experiences, memory, records, and so on. And to play those roles, it has to be axiomatic because it is not derived from other things. You have to be putting an axiom in the theory. And second, it has to be gnomic. It has to be a law of nature. And since it's not derived from other laws, it's a fundamental law of the world. Now, there's some potential questions here, right? If it is vague, then you have fundamental law that is vague law. And that seems odd, right? It seems odd that we have a theory in which everything else is exact, but this law is vague. Now you might think, what if I make this vagueness go away by writing down some very sharp boundaries on the borders of macro states and call that my preferred specification of the past hypothesis? That's consistent, but it's implausible. It commits you to something I call gratuitous or untraceable arbitrariness in nature. Unlike constants of nature, the precision of the gamma zero, right? So we have a precise version past hypothesis. But the precise version of gamma zero beyond a point makes no difference whatsoever to the velocity fields of particles or the probability of macro histories. The precision is kind of gratuitous in some sense. Unlike, say, gravitational constant G, right? In gravitational law, if you change the constant a little bit, the actual history would not be possible. typical histories would not be possible, given different values of G. But different boundaries of gamma 0, in general, small variations will not make a difference to how things evolve or in typical worlds or the probabilities of typical histories. And I explore this issue more in the popular version of the article called The Flaw at the Heart of Reality. I think the title is a bit unfortunate, but it is what it is. It's published in New Scientist in September. And a more academic version is this one called Nomic Vagueness on Archive, still on a review. Okay. Another issue is that the path hypothesis is a boundary condition. Not only that, it plays no dynamical role directly. It does not feature into dynamical equations. So in some sense, it's second class kind of law. So non-dynamical virtue and nature is not an issue here. So, all right, you have two potential issues with taking the path hypothesis to be axiomatic and nomic. If we don't take it to be axiomatic and nomic, we have a problem of explaining the various asymmetries in our experiences. Okay. The quantum versions, as Roddy mentioned, is almost the same in terms of mathematics, and the philosophical issues are similar as well. So you have a question of the status of path hypothesis in the quantum version, and it has non-dynamical virtue, that dynamical feature, dilemma between vagueness and arbitrariness. Also, there's something else here, as Katie mentioned. That is, in the quantum case, you have a dualism of two kinds of probability distributions. One, probability distribution due to quantum mechanics, the Born distribution in Bohm, in GRW. And the other is physical mechanical distributions of the path hypothesis. That is, you have to have x0 in gamma 0. And this one has to be typical by some typicality measure, or likely in some sense by some uniform distribution on phase space, right? Or in this case, Hilbert space. So you have two kinds of distributions here in the theory: quantum mechanical distribution and physical mechanical distribution. So for the sake of theoretical economy, you want to unify this into single kind if you can. All right. So that's the setup. My time is almost up. So I have to hurry up now. Now, the Wentaculus, that's the last part, and the innovation here. So what is the Wentaculus? Well, it comes from the neo-Boltzmannian physical mechanics that goes from Boltzmann and developed by people like Leibowitz and Goldstein and Roddy, among others. And the Wentaculus is a collection of density matrix realist theories with particular law, which I call initial projection hypothesis. Now, the theory is inspired by the Wentaculus. And Wentaculus goes back to David Albert and Barry Lower, but actually much earlier to a film by the Coen brothers called A Serious Man, in which the guy was asking someone's uncle in the basement, what are you drawing on a notebook with so many numbers? And turns out the guy is saying, I'm doing this probability map of the world, the probability for every event in the universe. And the idea is that the Wentaculus can do that. How? Well, the classical Wentaculus has the following feature. You have F equals MA, and the path hypothesis says X0 belongs to particular set gamma pH. But we know that gamma pH is not the exact set. It corresponds to a vague macro state M0. And given this one, you have uniform probability distribution over microstates compatible with gamma pH. And from this, you can evolve the probability distribution forward in time so that you can assign probabilities to every macro state at any time. That's how you get this probability map of the whole world. Now, you can extend this to quantum mechanics in the following way. You have the Schrodinger equation replacing F equals MA, and you have the quantum path hypothesis that says psi 0 belongs to a particular low entropy subspace of Hilbert space, HPH, that has low dimension relative to the rest of the energy shell. And given this HPH, we have this distribution of probability over the unit vectors compatible with this. And that's how you have the quantum Wentaculus. Now you can extend this to the density matrix version, right? So here's the density matrix extension. That's kind of naive extension, but also it's kind of a straightforward extension, right? How you can do it, it's actually possible. It's kind of cool. So you have the von Neumann equation replacing the Schrodinger equation. And we postulate that a density matrix version of the passive hypothesis. It says the initial density matrix is one among many possible ones compatible with the passive hypothesis. Or more precisely, is the one that the trace of W0 times the projection onto the passive subspace is equal to 1. This is entirely within the initial subspace. And moreover, you can construct this uniform measure over subspaces, definitions in this subspace by this very nice geometric construction that Rodi and I did this other paper. So this will be the straightforward density matrix version of the Wentaculus. But that's not a Wentaculus, okay? That's not a Wentaculus because it's not a real unification of density matrix in the arrow of time. The real Wentaculus, okay, so here's working up to the Wentaculus. So each psi pH quantum theory and each WPH quantum theory admits many choices of the initial quantum states. That is, the initial subspace HPH is compatible with many different wave functions and many different density matrices. Now, can we do better? Can we somehow narrow down the choice to exactly one possible quantum state given the subspace? Well, that's not possible given psi realism. It is possible given W realism, but it's not by this formalism of uniform measure over density matrices, but something else. So I propose that we have the following natural choice. I propose that we can use the pH, the passive hypothesis, to pin down a natural initial quantum state of the universe in the following way. So first of all, density matrix realism, the quantum state universe is given by density matrix that play a role in dynamics rather than a wave function. And there's a natural density matrix in HPH, the most natural one, I say, the normalized projection onto HPH. It does nothing to vectors outside HPH, but collects everything back to HPH. So this is the projection operator to HPH. And this is dimension of HPH. So now your density matrix. I call this the initial projection hypothesis, IPH. So here's a Wentaculus with only 2 parts, not 3. So use the von Neumann equation as the central equation of dynamics, how W evolves. Now the GRW version will have modification of this, but that's the central equation. The second part is replace both the passive hypothesis and the statistical postulate by this, the initial projection hypothesis that says in the temporal boundary of the universe, the density matrix is the normalized projection onto HPH, low-dimensional subspace for total Hilbert space of this. And there's no accompanying statistical postulate because there's only one possible density matrix compatible with this law. So nomologically speaking, there's only one possible quantum state at the universe at T0. Okay. Now you can develop realist versions of the Wentaculus by using this to solve the measuring problem, right? This framework. You can have the Bohmian Wentaculus, the Everettian Wentaculus, and the GW Wentaculus. All of them have very interesting features. Now the Bohmian one is like this. So you have the same guidance equation as the one shown to you by Rodi and Owen earlier, and the same von Neumann equation and the same distribution, but you add this particular initial projection hypothesis. It says W0 has to be this unique one. Now you can, if you have this, you can think of this as a Hamiltonian function in classical mechanics, giving you a velocity field. So you can rewrite this in terms of W0 and time evolution operators. So I'll show you that in a second. The Everettian version is like this. You have the initial projection hypothesis, the von Neumann equation evolving forward, and you have local variables given by the matter density function. That's my preferred version of the Everettian Wentaculus. So you can define a matter density function from the matter density operator and the WT density matrix. And the GRW version is given by Alori and co-authors. So this one, we have the WT plus given by a collapse of the WT minus, the previous time density matrix, given some collapse operators. And in a usual way, you define the distribution and collapse rate operators. And you also add this IPH to the theory. That is, W0 is the normalized projection to HPH. So from this moment, you have W0 fixed, you have collapses forward. So it's stochastic in this way. Okay. There's some surprising consequences of Wentaculus. Mathematically, it's similar to previous theories, but there's some surprising philosophical consequences of the Wentaculus. It helps us to see better the nature of the quantum state and the status of the initial low entropy distribution. Okay. So first of all, the universal density matrix. So propose that W0 is nomological, and later times Wt is derived from W0 for all time other than T0. So they mean by nomological. So W0 plays the following role. Think about W IPH Bowman mechanics. It's for concreteness. Same thing is happening, is the same for averaging version. With the Bowman version, W0 generates motion. It gives you a velocity field. It's simple because the path hypothesis is simple. It's fixed by the theory. So it's nomological necessary and does not represent things in ontology. That's what I mean by nomological, not ontological. So in contrast to position variables in WBM, they're ontological, right? The position variables Q represent things and properties in ontology, take on complicated values, do not generate motion, and are not completely fixed by the theory, nomological contingent. And in analogy with classical mechanics, you see that in classical mechanics, we have the following equations of motion: dp over dt and dq over dt, given by a Hamiltonian function. So the velocity field is given by taking derivatives of h. So h here generates motion. It is simple. It's a simple function of phase space variables, and it's fixed by the theory. If you change h, you change the theory. Now, the interpretation here is that h is nomological and not ontological, similarly to W0. So direct analogy with W0. The disanalogy is that h is time independent and Wt is time dependent. However, W0 itself is a fixed density matrix, like a fixed function, simple function. So W0 is more analogous with h. So here is the version of Bowman mechanics I want to use the nomological interpretation. So you see that we rewrite IPH and the guidance equation into one equation, the WIPH guidance equation, in which there's only one occurrence of W in the theory, that is in terms of in how it generates motion. So you don't need to invoke Wt anymore because everything else can be derived from Wt0 and the time evolution operators on both sides. So WQI over dt is given by this function. You can think of this as a complicated function of gradient of somehow Wt0. Okay. Now, function of this, right? In the averaging version, you have local variables mxt given by something similar, the trace of this evolved forward in time. These are both simple and mx function, mx operator. So give you kind of a function on spacetime. And this is a simple function. So I say this is a simple law, and this is a simple law. All right. By the way, just let me mention the idea of simplicity here. So the idea is that I assume the path hypothesis is sufficiently similar to be a wall. So the projection onto pH subspace is simple enough, does nothing to HPH. And the normalized density matrix is also simple. So that's Wt0. So I claim that the simplicity of this one and this one are on a par. Okay. Now, what about psi? What about making a similar move in psi quantum mechanics? Well, the move is not available for standard theories that take psi to be objective quantum state. Why is that? The simplicity of psi is not guaranteed by the simplicity of the path hypothesis subspace. So this is compatible with many different vectors. Specifying HPH takes much less information than specifying psi 0. Right? Think of specifying a vector or specifying an entire subspace. Right? But maybe there's some other route that's possible. Right? Maybe the related weight equation gives you another motivation to consider the simplicity of wave function. But anyhow, we have secured a pretty safe way to argue that a quantum state can be real by being like a law, by being simple enough, generating motion and so on. And that is good news for quantum state realism. It is one version of realism about quantum state. And this helps you to solve problems with human supervenience. So this goes back to Tim Maulin's objection that human supervenience is incompatible with quantum entanglement because quantum entanglement has to be fundamental and not separable. But if you have a law like quantum state W, it's simple enough. You can promote this from the ontology to nomology in the best system, such that the ontology is separable, but the nomology is not. The nomology is okay, right? The nomology supervenes on the ontology, and the best system is still simple. It is also compatible with the governing view of laws of nature, but I won't get into here now. Now, moreover, on the status of the interprojection hypothesis, that because IPH is directly involved in dynamics, we write it in terms of dynamical equations, right? So it does not face the dilemma between nomic vagueness and arbitrariness. Different choices W0 in general will give you different velocity fields in Bohm, or different matter density in Everett, or different probability of collapses in GRW. And that's good news for fundamental exactness. If you want to maintain that fundamental laws cannot be vague, right? Or cannot be arbitrary in some gratuitous sense. All right. And moreover, the probability dualism is gone too. We don't need to postulate for distribution over initial quantum states because there's only one possible choice, the W0. Right. So the only fundamental for distribution is the quantum mechanical one. And that's good news for theoretical economy. And by the way, this is good news for aberratants, or interesting news for aberratants at least. On my theory of aberratant Wentaculus, now there is a unique quantum history in the aberratant version, right? So the theory is only deterministic because you have W0 that's fixed by IPH, and you have a Norming equation fixed in WT and in time T bigger than T0, right? Bigger than T0. So this notion is that it's not just the future being fixed by the past, but also the entire history of the universe being fixed according to some precise mathematical scheme for all time. So on the aberratant picture of Wentaculus, the only thing fundamental is WT, right? And this gives rise to emergent multiverse, but that's not fundamental. WT is fixed by W0 and the von Neumann equation. So there's only one possible history, nomologically possible history for the quantum multiverse. And that's super cool, I think. And if you are more speculative and metaphysician, you might put this forward in terms of what I call the cosmic void, but I won't get into that now. Generalizations. What if the theory is not quite the quantum mechanical theory and not quite the Boltzmannian theory? But we can generalize this procedure to other kind of situations in, say, quantum field theory and quantum cosmology. So whenever you see a full Hilbert space, if that is given, that is big if, but it is given, then we can use simple principles, if there's any, to determine initial subspace H0 inside H, such that you can choose the natural quantum state by doing the same thing, projecting onto the subspace and be done. And that's a natural choice to be simple and unique. So you can get all these goodies by generalizing this procedure to other cases. In conclusion, all right, density matrix realism is theoretically fruitful position, and we only scratch the surface in this talk, but I show some of the fruits using the Wentaculus by showing that it does shed light on how to think about the quantum state, why is it real, in what sense it is real. And we'll talk about, the path hypothesis, can it be a law, can it be precise enough without being too arbitrary? So domain vagueness, strong determinism, probability monism, and then many more issues to explore, including empirical equivalence, different laws to consider, non-unitary laws. But in general, I think it does achieve this theoretical harmony. Lots of issues are in tension in my mind before I consider this view. But now lots of things are become more harmonious. So that, I think, is good news for the theory. So in conclusion, if the Wentaculus is true, then the laws of nature determine not only the time evolution, but also the initial quantum state. And that possibility is actualized by the initial projection hypothesis, which is the central part of the Wentaculus. All right. So here are some papers on arXiv, and that's the end of my talk. Thank you very much.